Okay, so today we are starting a new topic. So in week 1 we did algebra. Week 2 we've done equations and a fair bit with that. And so the next topic says relations and functions, but I'm just going to highlight the functions part because that's the bit that's actually important. Functions turn out to be the basis of a whole lot of applications of mathematics, especially in engineering and science. So it's the idea, the concept of a function that we're actually going to try and get you to understand, and to try and put into place, we're going to talk about relations to begin with, but that's not the important part. Okay, so the first part here says relations. So in here, all I'm going to do here is get a whole lot of terminology for you to become familiar with. And all of this terminology and notation comes from the theory of sets. Now, we're not going to talk about the theory of sets at all, but we do use the terms and the notation of sets because that's the way everything is written in terms of mathematics. So we need to be able to actually have a language that we can use. So I won't even highlight that box because that box itself isn't that important, but the idea of a set is, so just let's try and get an intuitive idea of what a set is. So a set is a well-defined collection of things. So that's pretty open. The things can be anything, and in mathematics we would call that thing an element. So for us, in this course, the things that we're going to talk about are actually numbers. So a set as a well-defined collection of numbers is essentially what we'll be talking about. And so I've said here, as an example, the collection of all real numbers greater than 4 is a set. Okay, so I've got a collection of things, real numbers, and this is well-defined. If I give you a number, you can tell me whether it's in there or whether it isn't. Is the number greater than 4 or is it not greater than 4? Okay, so we can tell. So in here we would have, I might call that set S just for the minute. So the curly brackets is our notation for a set. So the curly brackets means a set. This colon here is interpreted as such that. So this sentence would read, S is the set of numbers, and I use X just to refer to the numbers, such that the number is greater than 4. So that's a sentence in there, and that's how we would say that sentence. S is the set of numbers greater than 4. And I can tell, for example, that 10 is an element of that set. 10 is a number, it's greater than 4. And so I would write 10 is an element of, is that little symbol there. So is an element of. And likewise, I would say minus 1 is not an element of that set. So that's the notation and the words that we're going to use. As another example, I have here the collection of tall people. So in this case, the things are people, but that's not a set because it's not well defined. If I pointed to myself, am I tall? Well, that's open to interpretation. It's not well defined in here. So this thing is, the collection of tall people is not a set because tall is not well defined. Okay? Armed with that, that's all we need to know about sets. We will continually refer to things as sets, and we will write the things we're referring to in this notation here. Okay, so that's all you need to be able to do. We've got a little bit more terminology though. If A and B are two sets, then the union of those two sets. So union is a new word for us. This is the symbol for the union of two sets. And the definition is that the element, if a an element is in either A or B, then it's in the union. And the intersection of two sets, which has this symbol, that's when it's in both of the sets, both A and B. And so once again, we're not going to do anything more fancy than just use that terminology. So for example, if A is the set of 1, 3, 6, 9, 12, so forth, so that goes up, going on multiples of 3 there. And here I've got 1, 10, 20, 30, 40, B is a different set, then A union B with all those numbers that are in A or in B. So A union B would be, now 1 is in A, it's also in B, but I only write it once. 3 is in A, so it goes in, 6 is in A, 9 is in A. Now the next one here is 10, it's in B, so that's in the union. Then 10, then 12, 15, next one would be 18, then I would come to 20, 21, etc. I guess I should go dot, dot, dot. That would be the set of A union B. Get all the ones in A and all the ones in B, put them together, and just write the ones that are in both once. That's the union of two sets. The intersection of those two sets, A intersection B, you can see here that 1 is in both sets, so that's in there. 3, 6, none of those are. The next one would be 30, a number that's a multiple of 3 and a multiple of 10 in there. So I guess 60 would be in there, 90, dot, dot, dot. That would be the elements that are in both A and B. So that's all we need to know about sets. Just fit that on. Okay, so the next word or term that I'm going to use is that of a relation. And again, I'm not going to highlight the whole box, but I will just highlight the word. So a relation between two sets is a collection of ordered pairs. So I'll just highlight that. So an ordered pair is something that you've seen many times before, but you may or may have not called it an ordered pair. But something like, if I went here for example, is that up there? Yep. 2, 3 is an ordered pair. It's a pair because there's two numbers, and it's ordered because 2, 3 is different to 3, 2. The order in which I write them is important. Hence, it's an ordered pair. Now, we are used to interpreting our ordered pairs as points in our plane. So in here, a relation between two sets of numbers is a collection of points made up from those two sets, is essentially a way of thinking of it. So if I had two sets, 1, 2, 3, and 10, 15, 20, I could say, look, here's a collection of ordered pairs made up from numbers in here, where the x value, the first value in here, the abscissa, to use a big word on you, comes from A, and the second number in the pair comes from B, is what happens in there. And so this would be a relation in here. And what we think is 1 is related to 10, 2 is related to 20. So we would say 1 is related to 10, and 2 is related to 20. That's what that relation would tell us, yes? No, nope. I can make any combination of these whatsoever. Okay? Just some collection. So there are, an infinite number of possible relations in there, because I could go 1's related to 10, 1's related to 15, 1's related to 20, and whatever. Well, I guess it's not infinite here. But I can make up a whole lot of different relations, yeah? So, essentially, that's all I want to say. A relation is a collection of ordered pairs. Now let's get on to the ones that are of interest to us. So I'm going to say here, if I've got A is the set of all real numbers, so that means my first element in here can be any real number, and my second element there can also be any real number, then this equation would define a set of ordered pairs. For example, so here, if I let x equal to 1, then 1 squared plus 0 squared is equal to 1, so y would have to be 0. So that equation defines our ordered pair 1, 0. So 1, 0 is in the relation, is what we would say. Or alternatively, I could say 1 is related to 0. And so if I go through and find every set of ordered pairs that satisfies that equation, then I've found all the points in the relation. So let me do another one here. If I go 1, 1, 1 squared plus 1 squared is 2, so that's not in the relation. So we can see that this is well defined. We can work out whether our ordered pair is in the relation or not in the relation. It's in if it satisfies the equation. It's not in if it doesn't satisfy the equation. And let me do another one. Let me let x equal to a half here. And so I've got a half squared is a quarter. Y is equal to, y squared therefore equal to 3/4. So y is equal to the square root of 3 on 2. So that would be in the relation, because a half squared is a quarter, the square root of 3 on 2 squared is 3 on 4, a quarter plus 3/4 is 1, so that satisfies the equation. Likewise, I could say a half and minus root 3 on 2 are in the relation, because when I square a half I get a quarter, but when I square minus root 3 on 2 I also get 3/4. So a quarter plus 3/4 is equal to 1, so that works. So in this case, a half is related to root 3 on 2 and related to minus root 3 on 2. There's no reason why that can't happen. And if you were to actually plot all of the points in that relation, this is the graph that you would get. So you can see, for example, here, so I say, look, this is the graph of the relation, x squared plus y squared equal to 1. So graph of the relation here. You can see 1, 0 is there. You can see that 1, 1 certainly isn't on the graph. A half the square root of 3 on 2, so that would be the square root of 3 on 2, and a half minus the square root of 3 on 2. So you can see those 2 points are in the relation, and you can see that half is related to 2 different y values sitting in there. The story of why mathematicians like relations is a long one, and I would have liked to have gone through it, but time doesn't permit. So I'll allude to the story as we go through further as we go. A bit more terminology before we get into some really useful stuff. So here I have a relation, in this case between 2 sets of numbers, and I can draw a graph of that relation. For that relation, the set of x values that are in there, So let's just say the set of x values which are used, might be a good way of saying it, that's called the domain of the relation. Whereas the set of y values that up here is called the range of the relation. If you go back to this relation here, x squared plus y squared equal to 1, I can see that if I choose any x value between minus 1 and 1, just say I choose this one, there's definitely going to be a point associated with it. So there's definitely going to be a point in the relation that has an x value of whatever I chose there. So if, however, I went up to 1.5, there's no point in the relation that has an x value of 1.5. So 1.5 is not in the domain, whereas anything in here is. So we say in here, so the domain is, and this is where our set notation comes into play, it's the set of x values between minus 1 and 1. So the domain is the set of real numbers such that x is between minus 1 and 1 is the sentence that we say. That's what that notation is short for. That's the set of x values that appear in the relation x squared plus y squared equal to 1. This comes from our picture, so from the graph is how we saw this. We'll talk more about finding these things later, but for the moment, just trying to get the idea across. Likewise, the range, that's the set of y values that appear in our relationship. In our relation, I should call it. So, if I chose y is equal to a half, is there a ordered pair in the relation that has a y of a half? And the answer is yes. There's an x value here. You can see that that particular point is in the relation. Likewise, this one here. So there are a couple of points in the relation that have 0.5. So that value is one of the values that appears in the relation. In fact, for any y between minus 1 and plus 1, there will be a y value. There will be a point with that y value. So the range is also the set of real numbers between minus 1 and 1. For any other y value, there is no ordered pair in the relation with that y value. So let's do another relation. It says find the domain and range of the relation defined by this equation, x plus y equal to 2. Now you look at that and you say, yes, I know what that is, hopefully, because you recognise that as a linear equation in two variables. So therefore you know its graph is a straight line. And in fact, if I were to write that as, so just to say here, I could rewrite this as y is equal to, I'll say minus x plus 2 might be a good way to rewrite it. And then that would say, this is a line whose y-intercept is 2 and whose slope is minus 1. So every time I go across 1, y goes down 1. So there are 2 points on the line, and so I can actually graph this one. So there's the graph of that. So this is the graph of y is equal to minus x plus 2. So there is a pictorial representation of all the ordered pairs in this relation. And you can see that no matter what x value you choose, if I choose this x value, there will be a point on the relation. Right? This goes forever in both directions. So in this case, the domain is every real number. So the domain is equal to the set of all real numbers. Now, as you can imagine, mathematicians get sick of writing down set of all real numbers all the time, and so we have a symbol for it. And we tend to use the Blackboard R font, if you like. That's the Blackboard R, meaning the set of all real numbers. Sometimes you will see a bold capital R used. But for handwriting, you can't tell the difference between something bold and something not bold. So for handwriting, we certainly use that. So now, if I pick a y value, is there an ordered pair in the relation that has that y value? And the thing is, it doesn't matter what y value you choose, I will be able to find an associated point that has that y value. So the range will also be, in this case, the range will also be the set of all real numbers. In both of these examples, the domain and the range was the same set. That's purely coincidence. Okay, we'll come across some shortly where that's not the case. I presume back here that we are assuming that you know that this is the graph, or this is the equation of a circle in here. So when I have x squared and y squared, the graph is a circle, and in this case it's a circle with centre 0, 0 and radius equal to 1. I know that crops up again later on, so basically we're just going to hope that you can recognise that.
Are you saying if it wasn't a 1, are you saying that a 1 is the size, is obviously the size of the circle?
Is the radius, yes. If I wrote it like this, it would make it clearer. Because later on, when I'm going to have an x squared plus y squared is equal to 4. That's 2 squared, so that's going to have a radius of 2. Yeah. Oh, look, I'll put it in here. The actual general equation of a circle is x minus a all squared plus y minus b all squared is equal to r squared. So that has centre AB and radius r. So that's the general equation of a circle. I found that a fair few times in the notes actually, where things just crop up, and I presume that when the notes were written it was assumed that you would know it. This is one of them. There's a couple of other places as well where that happens. But anyway. So if you don't follow something, ask, I guess, is the key.